Hello, welcome to Chapter 8.1, Part 2 of Euler Diagrams. Here we're going to look at numbers. Now, it's a little bit more straightforward with numbers. So let's look at all numbers. And we saw this briefly earlier when we were talking about the counting or natural numbers. And recall that these numbers are the set 1, 2, 3, 4. And these numbers were all part of the whole numbers. So remember, the natural numbers were inclusive in the whole numbers because the whole numbers we added in the 0 plus the natural numbers. So how would we draw this diagram? Well, let's see. Here we have the natural numbers, 1, 2, 3, 4, to infinity. And then we have the whole numbers where we add in a 0, which makes the set a little bit bigger. So the natural numbers are a subset of the whole numbers, and that would be how we would look at the Euler diagram of that. In example number 7, where we're going to ask ourselves a question about certain numbers that we looked at earlier. So we want to ask, where do the square numbers go, the Fibonacci numbers, and the triangular numbers? And it turns out that these are natural numbers. So they would be part or a subset of the natural numbers set. So you can think of them as circles inside the natural numbers or subsets of the natural numbers. Now, in this case, we're going to use our knowledge of sets of numbers to determine which statement is correct. All integers are whole numbers, or all whole numbers are integers. Let's look at the following: where the rational numbers would go and where the irrational, and would the irrational numbers overlap the rationals or not? And then, of course, where would the natural numbers go? Well, we kind of saw something like this earlier, and it turns out that the irrational numbers do not overlap. But the natural numbers are the most inner, and then if we add 0, we get the whole numbers. And then if we add on the negative numbers, we get the integers. And we saw that earlier. So if we were to look at the real number system, we see, as I just mentioned, the irrational numbers are not within the main diagram here. They're outside of the main diagram because they do not overlap the rational integers, whole numbers, or natural numbers. Recall that these make up the real number system. So we see that the irrational numbers are real numbers, but they are not a subset of any of the other number types. So now we're going to place elements inside the Euler diagrams. And as mentioned, Euler diagrams, you can place an element in more than one place. So suppose we know a cat named Fluffy. Where in the circles for some cats are pets do we place Fluffy? Well, note the whole set is using the circle. So here we have Fluffy. Fluffy can be a pet, cat, but Fluffy can also be a cat that isn't a pet. So, for example, Fluffy can be a lion. A lion, despite what you may have heard on The Lion King, Fluffy, a lion, is not considered a pet cat. So we can put F here too. If Fluffy turns out to be a lion cat, well, then Fluffy would be here, but Fluffy could also be a pet cat. So we use F to represent Fluffy. Fluffy is a cat, so it must go somewhere in the circle of cats, but as mentioned, Fluffy may or may not be a pet cat. In the Euler diagram, if we're not sure where the object goes, we can place it in all the places where we think it could go. And this is in contrast to Venn diagrams, where we know exactly where each object goes, and we always place each object in only one place. So looking at question number 9, we draw a picture showing the logical statement: all cats are animals, Fluffy is a cat, and Buster is an animal. Well, let's see. how would we describe this in an Euler diagram? Here's animals, here's cats. All right, so we know Fluffy is a cat. That's made very, very clear. And we know we have the animals, and we know cats goes inside animals. But Buster is an animal, but it could turn out that Buster is a cat. Buster could be the name of a cat, or Buster could be the name of, let's say, a snake. A snake is an animal, but a snake certainly is not a cat. So now we're going to draw another picture using Euler diagrams to discuss a logical statement. So no ducks are blue, Fred is a duck, and Cindy is not blue. Well, we see blue things, and we put two separate circles because they do not overlap since ducks are not blue. Fred is a duck, so Fred definitely goes into the duck place. Cindy is not blue, but Cindy can be a duck, yes. Cindy can be anything else. Cindy could be a cat, Cindy could be a dog, or Cindy could be a person. Who knows what Cindy is? So we can put Cindy here in the empty space. A little key to remember or to help you, so to give you hints on how Euler diagrams work, here's the all statement, here's the sum statement, sum A or B, and then here's no A or B. So let's see how we can use our quote-unquote quick key. So suppose Fred is in A. Here's where he would go in each picture. Fred is A, so he's inside. He's a subset of a bigger set. If Fred is in A, he can be either in the intersection of A or outside of an A, like, for example, the pet cats and the cats that are not pets. Or Fred can be part of a set A that does not intersect with B. For example, this would be purple things, but Fred is a yellow duck. Now let's suppose Fred is in B. Well, where would he go in each picture? Fred is an animal, and Fred can be, but we don't know what Fred is in B, and we don't know, so he could be in A or B. Fred, like before, above here, he could be in the intersection, or he can be outside of the intersection. And here, similarly, Fred can be in the set here, but it does not intersect there. It turns out that he could be in two places because B has two parts to it. So here, this is the reason, let's look more closely at this one, that suppose Fred is in B. We know that Fred is something in B, and we also know that Fred could be also in A, because there are two parts to this. So Fred could be in either A or B. We can only figure out if we're more specific about what Fred is and what we're talking about in that particular diagram. Now lastly, let's suppose Fred is not in B. Where would he go in each picture? Fred is outside of B here. He's not in A, he's not in B, he's outside. Just like when we were talking about the student who didn't like fried or roasted food. So that would be a similar situation here. Similarly here, if Fred is not in B, well, Fred can be outside of A and B, or Fred can be in A. But he wouldn't be in the intersection because then he would have to be part of B. And then, of course, again, here he can be outside of A and B, or he can be inside A. So in the first one, Fred can only be in one place because not B means not in A either. Thank you very much. I hope that you enjoyed this video. Be well, take care, and goodbye for now.